Okay, so this means M1 intersection M2 intersection MT. This is contained in M, right? So this means from prime avoidance lemma in commutative algebra, that was in chapter 1, proposition 1.11 or 110 in Atia McDonald, that it means that sum of if mi should be contained in M, right? But now, by the maximality property of prime ideal mi, we should have mi equal to M. So it means that there can't exist any other or different maximal ideal M which is different from the set of maximal ideals M1 up to MT. So therefore, collection of maximal ideals or all set of all maximal ideals in A are actually finite. So hence the theorem, hence the proof of the claim 2. So now let's go to the claim 3. So claim 3 is the final statement which says that there is at most D maximal ideals, which is ultimately the statement of the problem which we are proving. Actually, there is an at most D maximal ideals in A. Okay, so let's prove it. So suppose the M1 up to MT are collection of maximal ideals, all maximal ideals. Now we know that the collection of maximal ideal is a finite set. So we assume that this is the collection of all maximal ideals in A. So now therefore the Jacobson radical of A, which is intersection of all maximal ideal, is basically this finite intersection of this finite collection of ideals I equal to 1 to T. Okay, so now A over J, this is basically A over intersection of I equal to 1 to T Mi. This is isomorphic to A over M1 cross A over MT. And why this is isomorphic? This follows from the Chinese remainder theorem. This part of the isomorphism follows from Chinese remainder theorem. And why we can use the Chinese remainder theorem here? Because any two MIs are co-maximal, so they are basically co-prime to each other. So therefore, we can use the Chinese remainder theorem. Hence, the map is surjective, and this map is an isomorphism. So now, if we look at each of the A over Mi, each of A over Mi, these are all field, right? Because MIs are maximal ideal. So these are all field. Let's call it over Ki. Now I'm saying that each Ki is a finite field extension of K, of the field K. So now, like K is the underlying field which is given. So Ki is the finite field extension of K. So now, why Ki is finite field extension? Because now I'm applying the Zariski lemma here. So the Zariski lemma actually says that if A, or let's call it L over K is a finitely generated algebra, and L is a field, then L is a finite extension. That means it's a finitely generated module over finite dimensional vector space over K. Finite L is a finite extension of K, right? So therefore, by Zariski lemma, we can say that each of the Ki, because A is finitely generated algebra over K, since it is an affine algebra, therefore each of A over M is a finite extension of K, since it's field and as a finitely generated algebra. So now we know that if W is a vector space, if W is a vector space which is finite dimensional vector space over K, then W is isomorphic to some K power M, right? So in this case, each of the field Ki, which is a finite extension of K, therefore finite dimensional vector space over K, is basically isomorphic to K power some Di, where Di is the dimension of each Ki over K. Hence, A over Ja, this is isomorphic to K1 times K2 cross Kt. This is basically K power D1 plus, sorry, into K power dt. So this is basically K power D1 plus D2 plus dt, right? And so therefore dimension of A over J over K is equal to D1 plus D2 plus dt. Yeah, here one thing which I forgot to mention, that is the thing that dimension of A over J. So since A is a finite dimensional vector space over K, A over J is also a finite dimensional vector space over K, and moreover dimension of this is less than equal to dimension of A over K, which is equal to D, right? And this is because I'm not going to prove this, because this is quite easy to see. Like the elements which generates A, they will also of course generate A over J, because whenever we are quotiented by JA, we are actually kind of what should I say, doing the modulus through the J. So actually grasping some element from A. So therefore the dimension of A over J will be less than that of dimension of A over K. Intuitively it is quite clear. Less than equal to, sorry. Hence from here we can say that this d1 plus d2 plus dt, this should be greater than equal to 1 plus 1 plus 1, because d1 d2 dt will be at least 1. So this is equal to actually t, since it's t times 1. Hence dimension of K over A, this is D, which is actually greater than equal to dimension of K of A over J, which is actually greater than equal to T. This implies D will be greater than equal to T. Hence T, which is the number of maximal ideals in the ring A, is less than equal to, or is bounded by the number D, which is dimension of A over K. Hence there can be at most D maximal ideals in the ring A, like in the affine algebra, K algebra. Hence the proof of the part C, like claim C, which in turns complete the whole proof of the problem. So here also I want to mention one more thing, which is that in the claim 2, I used the fact that the concept of Barton ring by means of that it's a Noetherian ring and of dimension zeros, then hence it is Artin ring, hence has a hence the set is, which is a collection of some maximal ideals, will have some minimal elements. So I don't think that it's, later I realized that I don't need to actually use the fact of a concept of Artin rings in this case, or Noetherian also, because there is one proposition I have found, like which you can prove actually, that in a commutative ring any collection of primordials has a minimal element. Yeah, here's yeah, any collection of primordials will have a minimal element. So S is collection of maximal ideals, so therefore it will have a minimal element, and of course the minimal element will nonetheless M1 intersection M2 intersection MT. Okay, hence the theorem. Thank you for listening to me. Thank you so much.